Okay, these are some more problems from section 9.3, and what we just want to do is write the the Maclaurin series for this given function, and I've seen some of these in the AP exam where they have you combine these functions, and one of them is a series, and one of them is just a kind of a partial series, so they'll simplify in a nice manner, and so this is a good example. So we've got sine of x minus x plus x to the third over 3 factorial. So, you know, if you didn't have any experience with this, you might kind of not know what to do, but we could just expand sine of x out. I think they wanted you to write this as a series anyway. So this is the sine of x. This is from good old page 491, our table of Maclaurin series. And then I just minus x and x to the third over 3 factorial. And you can see that these x's cancel, and these x to the third over 3 factorials cancel, becomes 0. And this is what we have. Okay, now you could write it like this, and if you're going to do a summation, you know, your summation would have to be going from n equals 2 to infinity, because if I put 1 in here, I'm not going to get the 5. If I put 2 in here, 2 times 2 is 4 plus 1 is 5. That's 5. Okay? And 2, negative 1 to the second power is positive. So that work out. You could also note here, by replacing n with n plus 2, the general term can also be written as this. And that would work when n equals 0 then. 2 times 0 is 0, plus 5 is 5. Same thing, 5, and then negative 1 to the 0 power is 1. So that would also generate it, so it depends on how you're going to do your index. Okay, number 7. This was pretty straightforward. This is our good old x times e to the x, and we know we can multiply. So series by x, and it won't change it gives you a new series, but it's a valid way to find a new series. It will generate a new series, and it also have the same radius of convergence. So if I multiply, this is my e to the x, here's my e to the x series, go to 1 plus x squared over 2 factorial, x to the third over 3 factorial, etc., x to the n over n factorial. Then if I multiply everything by x, this becomes x squared, x cubed, and if I multiply x to the n times x, that becomes x to the n plus 1. So there's your new series, so that was pretty easy. Okay? And then number 8, we have to use a trig identity. They gave you the identity, and I derived it again just to check it. And this is some of the techniques we used for integration and use substitution when we were doing section 6.2. You had to use a substitution, and I just derived it again, cosine of x plus x, which is the cosine of 2x, cosine, sine, cosine squared minus sine squared, which is one of the basic forms of the two-angle formulas for cosine. And then we get everything in terms of the cosine, because I want cosine squared. So cosine, then the sine squared is 1 minus the cosine squared. And this is the negative 1 plus cosine squared, and that's 2 cosine squared x minus 1. Put the negative 1 on the other side, make that positive 1. Divide by 2. There you go. There's another form of the two-angle formulas. Okay? Actually, I think this is the formula I've seen in books before. And then we adjust it. Okay? And if you do this a lot, then it just becomes second nature. So if you have to use it on a test and you actually forget exactly all the little nuances of the formula, then you just derive it and you've got it. Okay? So this is what we've got. So I wrote cosine squared of x like this, and then I just broke this up, 1/2, and then 1/2 cosine 2x. And I wrote it like this. So this is using the trig of trigonometric identities, this is equivalent to cosine squared x. And I just know my cosine series from 491, and I just, instead of cosine of x though, every time there's an x I put a 2x, and I can expand it like that. So there you go. There you have it. And then I just multiply it out. 1/2 times 1 is 1, and then etc. And we're multiplying by a positive, so we're not going to do anything with this negative 1 to the n power. Okay, so when I use the distributive property and distribute this out, the other thing is that each denominator has a factor of 2 now added to it, or times it. But what's 1/2 plus 1/2? That's just 1, so that's nice. That simplifies nicely. And then this 4x squared over 4 was just the x squared. And this is 16x to the 4th. 2 to the 4th, x to the 4th. So that's 16x to the 4th over 4 factorial, which is 24. 2 times 24 is 48. 16 goes into 48 3 times. etc. And then we've got this. Now, what did I do with this 2 on the bottom? What we did was we changed this 2x to the 2n to 2 to the 2n, x to the 2n, and then we can take the 2 and 2 to the first power and put it in the top to make it 2 to the negative 1, and then we can multiply these. So 2 to the 2n times 2 to the negative 1, we just add the exponents, we get 2n minus 1. So it simplifies like that. So that's your general term. Okay? And number 9 is done the same way, except we're going to just use the two-angle formula and get everything in terms of sine squared of x rather than cosine squared of x. So that's what we got over here. Let me fix this for you. There you go. And I kind of wrote out some of the derivation. It never hurts to do this so you remember, so you can do it really fast. Cosine 2x, cosine squared, sine squared. And then I get everything in terms of the sine squared, so 1 minus the sine squared minus the sine squared. So 1 minus 2 sine squared. Put the 1 over here. Use the negative sign. Change it to the order. Multiply by negative 1. And then divide by 2. And here we go. So same idea. A little bit different because we got a negative sign. So that changes it around a little bit. That causes some more kind of issues here. Okay. So I'll multiply out using my distributive property, and again I'm going to have a factor of 2 in the denominator, except that this negative sign is going to cause my signs to alternate and change. So this is going to be a negative, times a negative is positive, that's going to be a negative, etc. When we come all the way out here, this is going to change this index. To make this work, you'll see that this has got to be negative 1 to the n minus 1. Okay, because I'm changing the signs again. So that would change the signs. Shift them over 1. And this is the same. And then I kind of wrote this as they did in the cosine. I kind of wrote it on this step. 2 to the 2n, x to the 2n. So I can move this 2 up there. But, see, the thing is that I've got 2 now minus, I'm 1/2 minus 1/2 cancel, so that I just lose that term. So I've got x squared, and then this is just 4x squared over 2 times 2 factorial. Okay, and then it's over here. This is it's shifted over. So this is 4x squared over 4, which is just x squared, and then this is 16 x to the 4th over 2 times 4 factorial. That's again 24 times that's 48. 16 goes into 43 times. So it's very similar, but we usually need to have like about 3 terms. So I figured out my next term. I kind of did it over in pencil. The next term would be 2x to the 6th over 6 factorial. And then times that 2 from the 1/2. So I worked it out and I came up with 2x to the 6 over 45. That would be the third term. So I can see the 3 terms. And then we got the 1, negative 1 to the n minus 1. That's the shift because of the negative sign. And then we took this negative, this 2 in the bottom and put it up on the top like we did in the cosine. And we have 2 to the 2n minus 1. X to the 2n over 2n factorial. And then again, you can fool around with the index to make this work by replacing n with n plus 1. The general term can be written as this. So go back and change that. Just every time you see an n, you put an n plus 1. So if you've got 2 times n minus 1, you've got 2 times n plus 1 minus 1. Okay, so that would be 2n minus 2. Okay, well, I'm sorry, 2 times n plus 1. So 2n plus 2, okay, minus 1 is the 2n plus 1. So every time you see an n, you put just a n plus 1. Okay, so that shouldn't be too bad. So they give you the general term if you make that substitution. And then number 10, x squared over 1 minus 2x. Now right away, boy, that 1 minus, this should kind of pop right out to you. It's our good old geometric series. And we've got that in our Maclaurin's tables. We got 1 over 1 minus x. So instead of writing an x, I put a 2x. So my ratio is 2x, and my first term is 1. So I'll just separate this, and I'll bring the x, factor the x squared out. I'm going to multiply x squared times this series, and I'll get this series for this, the Maclaurin series for this function. And my ratio is 2x, so I start at 1, then multiply by 2x, then multiply by 2x, multiply by 2x. Okay. And we could change this to be 2 to the n, x to the n, because we're going to multiply everything by x squared. So that's going to be x squared, 2x cubed, 4x to the 4th, I've got the x squared times x squared, and then 2 x to the 5th. Well, I'm sorry, 2 cubed is 8 x to the 5th, and then all the way out there. And then I wrote this as 2 to the n, x to the n. So when I multiply it by x squared, the 2 to the n stays the same, but x to the n times x squared, okay, what we do is we add, so that would be x to the n plus 2. Add the square. And there you go. So that's number 10. So those are just straight Maclaurin series. Hope that helps.